Okay, so let's have a look at this question here. It says f of x is equal to 2x over x squared plus 3, where x is an element of the rows. It says find the set of values of x for which f dash of x is greater than 0. You must show your working. Solutions based entirely on graphical or numerical methods are unacceptable. So for me, looking at this question, the first thing that I notice is that it says find the set of values of x. So straight away, what that tells me is that my final answer is going to be an inequality. Yeah, that's the first thing that I notice. Okay. Now it says for which f dash of x is greater than 0. Well, f dash of x is just a derivative of f of x, isn't it? So for us to be able to answer this question, we need to differentiate. Now we are faced with a rational function here, a fraction. So the way we differentiate fractions is by using the quotient rule, isn't it? So let me just write this here. Quotient rule. So just to remind you, if y is equal to u divided by v, then dy dx, right, or f dash of x, no matter what notation you use, will be v times u dash minus u times v dash over v squared. So all we've got to do now is just apply this to the function we have. So let's write this here. But f of x is equal to 2x over x squared plus 3. Quite clearly, we can see that u is equal to 2x, the numerator, and v is equal to x squared plus 3, the denominator. So then u dash, we differentiate this. This will give us 2. V dash, we differentiate this. This will give us just 2x. So then we're in a position to just apply this to the formula. So I'm going to use f dash of x instead because we're using that in the question. That would mean that we've got v times u dash, right, which is going to be 2 multiplied by x squared plus 3 minus u times v dash, which is going to be 2x multiplied by another 2x. And then this is all going to be over v squared, which is going to be x squared plus 3 all squared. Okay, so now this is our f dash of x, right? What we should do now is just attempt to simplify and tidy up where we can. So if I look at the numerator, I can expand that. That will give us 2x squared plus 6. And then this will give us minus 4x squared, isn't it? So now if I tidy this up, then this is all divided by x squared plus 3 all squared. Now we don't need to expand the denominator. That's fine. The numerator though, this just becomes a 6 minus 2 minus 4 is a minus 2, isn't it? So this is 6 minus 2x squared on the top over x squared plus 3 all squared. So now we've got our expression for f dash of x, right? What does the question ask us for? For when this is greater than 0. So let me just write this here. We're looking for f dash of x when this is greater than 0, which means that we're looking for when this here, this function or this expression is greater than 0 too. Now, we have a fraction here, so we've got to be careful, right? You have to ask yourself, when you're dealing with a fraction, when can a fraction be positive, right? You could think of it as, well, if I have two positive numbers, sorry, then this is always going to give me a number which is greater than 0, right? Or the other solution, or the other option is when they're both negative, right? The numerator is negative and the denominator is also negative. This will also give me a positive number. So we need to ask ourselves, well, do any of these, right, apply? Yeah. Now, the first thing I notice is that if I look at the denominator here, this is x squared plus 3. So let's just analyze that. We've got x squared plus 3 here. Now, if I was to sketch the graph of this, then we know that it's just going to be a parabola, right? And the y-intercept will be at 3, isn't it? It's just moved 3 upwards from the graph of x squared, right? Now we can quite clearly see here that this is always positive for sure. Yeah? Always positive, right? So I can say for sure, right, that then if I just look at this here, I've got 6 minus 2x squared over something which is always positive, right? And then on top of that, I'm also squaring that, aren't I? So when I square something that's always positive, that will always give me a positive number. So therefore, we can say for sure that the denominator of this here is always positive. So then if that's the case, remember, we're looking for when this fraction is always positive altogether. We know that the denominator is always going to be positive. So for it to be always positive, the entire fraction, we would need the numerator to always be positive too. So what we need to then look for is, well, the numerator, which is 6 minus 2x squared, this has to be positive as well, right? So then you just say, well, this is just a simple quadratic inequality. So you're just going to solve this now. So let's do it. We're going to move the minus 2x squared over. So it gives us 2x squared here. We're going to divide 3 by 2 to give us 3 is greater than x squared. And obviously, this is just the same as saying x squared is less than 3. Now, no matter how hard or easy a quadratic inequality is, always, always, always draw a sketch. So that if I sketch this here, then we are sketching the graph of y equals x squared, which is just a parabola, like this. And we're asking for when this graph of x squared is greater than 3. So we need to draw the graph. This is y equals x squared. We also need to draw the graph of y equals 3, which is just going to be a horizontal line, isn't it? I mean, like this, around here. Yeah? So we need where the graph is less than that. And we can see it's for values, right? Between here and here, right? And we can see clearly the values will just be the intersection points of the graph of x squared and 3. So you just need to solve that. So we'll have x squared is equal to 3. That means that x is just equal to plus or minus the square root of 3. So therefore, you're going to have this here as positive root 3. You're going to have this as negative root 3 here. And you can see quite clearly the values of x for which this here is less than 3 is going to be for values of x which are between negative root 3 and positive root 3, right? So then to conclude, remember what we were doing? We were looking for where the entire function was always positive. We concluded that the denominator was always positive. So therefore, we had to just look for the numerator, the values of x in the numerator for where the function is always positive, right? And that was for values between minus root 3 and root 3. So this here is your final answer.